Welcome to The Explainer. Today, we're diving into the epic journey of a single sugar molecule. Now, this isn't just some abstract story. It's happening trillions of times a second inside your body right now. It is the fundamental process that powers pretty much everything you do. So think about it. You eat something, maybe a piece of fruit, and somehow that sugar becomes the energy you need to think, to move, to just be alive. But how? How does that transformation actually happen? Well, the answer is a tiny, 10-step adventure called glycolysis. So let's meet our hero for today, a 6-carbon molecule called glucose. Glycolysis is its story, its transformation. It's the very first stage in this grand quest to unlock the energy that's packed inside of it. The whole goal? To split this one big molecule into 2 smaller ones and, harvest some precious energy along the way. Okay, but before this grand journey can even kick off, our hero, glucose, has to face its first big challenge. It's just floating around in your bloodstream, but all the action, all the magic, happens inside your cells. And it can't just waltz right in. You see, the cell membrane is basically this fatty, oily barrier. Glucose, on the other hand, is water-soluble. And as we all know, oil and water, they just don't mix. So glucose can't just slip through. It needs a special escort, a kind of cellular doorman, to let it inside. These doormen are called GLUT transporters, and they are all over your body. There are even these cool little mnemonics to help you remember where they are. Like GLUT1 is for blood and the brain, but the one you really want to pay attention to is GLUT4. It's in your muscle and fat, and here's the kicker. It's insulin dependent. It only opens that door when insulin rings the doorbell. All right, glucose made it. It's inside the cell. The adventure can finally begin. But like any great quest, this one requires a little upfront investment. Before the cell can actually make energy, it has to spend some energy first. So the very first thing the cell does is trap that glucose molecule so it can't just change its mind and leave. Remember how those transporters can work both ways? To stop our hero from escaping, an enzyme comes along and, bam, slaps a phosphate group onto it. This acts like a molecular ball and chain, totally changing its structure and locking it inside. This step is irreversible. There's no turning back now. And of course, that move costs something. That phosphate group was ripped right off a molecule of ATP, which is the cell's energy currency, so just like that, we're 1 ATP in the hole. Okay, a few reactions later, another super important enzyme called PFK1 makes the final investment. This is the committed step of glycolysis. It slaps on a second phosphate group, making the molecule even more unstable and ready for what's about to happen. Once this happens, that glucose molecule is absolutely 100% committed to finishing this pathway. And you guessed it, that second phosphate also costs energy. So now we've spent a grand total of 2 ATP molecules. Our investment has officially been made. But hey, every good investment expects a return, right? And this is where the payoff begins. The cell has spent its cash, it's primed the molecule, and now it's time to start reaping the rewards. With those 2 phosphate groups making it super unstable, our 6-carbon hero gets cleaved right down the middle. An enzyme called aldolase acts like a molecular axe, splitting it into 2 separate 3-carbon pieces. Now this is the key. From this moment on, every single reaction happens to both of these molecules at the same time. Everything is doubled. The payoff phase is just this flurry of action. First, high-energy electrons get ripped off and captured by a molecule called NAD+, creating 2 NADH. Think of these as little energy shuttles. They're going to be cashed in for a ton of ATP later. And then, in 2 different steps, we finally get our payout in cold, hard ATP. And here it is, our first return on investment. In one step, the cell generates 2 brand new molecules of ATP, one from each of those 3-carbon fragments. We've officially broken even. And then, in the very last step of the whole pathway, we get our final payout. Boom! Another 2 molecules of ATP are made. This is pure, sweet profit for the cell. So, Our original glucose molecule has been completely transformed. It's now two molecules of a substance called pyruvate. Its 10-step journey is over, but now it faces a critical choice, a fork in the road. And what happens next depends entirely on one thing. Is there any oxygen around? If oxygen is present, we call that aerobic conditions, pyruvate moves on to the next, much bigger stages of energy production where a massive amount of ATP is going to be generated. But if there's no oxygen, anaerobic conditions, think super intense exercise, pyruvate takes a totally different path. It gets turned into lactic acid. You know that burning feeling you get in your muscles? Yeah, that's this pathway in action. This emergency detour is all thanks to a key enzyme, lactate dehydrogenase, or LDH for short. When oxygen is low, its job is to grab that pyruvate and quickly convert it into lactic acid, which allows glycolysis to keep cranking out just a little bit of energy. And this is where it all gets incredibly real, especially in medicine. That same enzyme, LDH, is a critical biomarker. When doctors see high levels of LDH in a patient's blood test, it is a huge red flag. It tells them that somewhere in the body, tissues are starved for oxygen and are having to rely on this emergency pathway. It can be a telltale sign of really serious stuff, like a heart attack or restricted blood flow. So after that epic 10-step journey through the investment, the payoff, and that final choice at the fork in the road, what's the final treasure, our hero glucose 1 for the cell? Let's check out the final balance sheet. Okay, so we started with one molecule of glucose. We invested 2 ATP, but we made 4. So that's a net profit of 2 ATP. We also created 2 of those high-energy NADH molecules, which are kind of like winning lottery tickets we can cash in later for way more energy. And of course, we're left with 2 molecules of pyruvate, ready to continue the quest for fuel if there's oxygen. So if you take one thing away from this whole journey, let it be this. Glycolysis basically proves a fundamental rule of life. You've got to spend energy to make energy. The cell had to make that initial investment to unlock a much, much bigger payoff down the line. So we've netted a couple of ATP. That's great for a quick burst of energy. But you have to remember, this is just the beginning. This is just step 1. Those 2 pyruvate molecules hold the potential for so much more. Which leaves us with one final big question. What happens next? What happens when there is oxygen and the real energy production begins?